Hi everyone, and welcome to the tutorial of statistical mechanics. Today we're going to study Bose-Einstein condensation. So, to begin, we need to think about a system of three bosons or a gas composed by bosons, and we want to count the number of particles on the system, right? So a way to do that is to sum up all the energy levels from 0 to infinity of the occupation of bosons on each energy level, right? So how do we do that? Do you remember what's the value of this quantity of the occupation average? So it's just beta mu epsilon minus mu minus 1, right? Okay. And can you tell me when does this sum becomes maximal? Like what values of mu gives me the most contribution? It's when mu is 0. Okay. Epsilon is a function, so epsilon can, we have it here, right? So at some point we will get it, but this is bigger when we get mu that mu goes to 0. In other words, what is mu? Mu is the cost of adding a particle to the system, right? In other words, if the cost is 0, then we should get as many particles as we can get, right? So, do you know how to solve this sum? So me neither. You have to go to the integral, right? And when we go to from a sum in energy to an integral, what do we have to add to our density of state? Yeah. Okay, great. So after doing a lot of change of variables and putting a lot of things that you did during the lecture, so when mu goes to 0, just let me. This implies that E to the mu beta goes to 1. Do you know what this term is called? How do we call this term? This is the fugacity. Maybe you see it in the lecture. You already saw Bose-Einstein, right, in the lecture?
Right.
Okay. So from here, Okay, so after doing all the change of variables into this, like we are sending e to the beta mu to 1, and then we are changing variables. And here, as you can see, we have included that the density of states goes as epsilon 1 half, right? Which is the free particles on a box in general. I know it's a big step, but do you have any questions of how I get from here to here? Okay. This is the thermal wavelength, right? We saw in previous tutorials. So just to remind you. And just erase this. Maybe as a note here. And this is the. Do you know this integral? I think you saw it in the lecture, maybe. This is the Riemann zeta function. Okay. So this thing is actually. Okay, let me just plug here Riemann zeta function. Okay, so this is the Riemann zeta function, which is defined as 1 over gamma times this integral. I don't know if you know, but there's a problem associated with the Riemann zeta function. If you can find that all the zeros that are not trivial have a real part 1/2, you will win $1 million, like this. There's a prize associated, and also a Fields medal, and a lot of things. It's probably the most important problem open in mathematics. So from here, you can see that we have gamma and it's not C, it's okay. I don't remember the name of this letter, but we have, instead of P, for us P is 1.5. So the average number of particles is then So I just want you to be on the same page. Here there was an integral that it's actually a triple integral, right? And then I got with the Jacobian. You can see it from here. Like this 4 pi is a very good. Like whenever you see 4 pi, usually it's because of the volume of the surface of the sphere. So I just took this formula and then I plug gamma up here, and this is exactly the integral that we have. Sorry, here I missed the dx. Right. Okay. So, as you can see, we have this number for the
first function, like we have gamma of 1.5 and the one.
yes.
This is gamma, and what is this, the middle one?
This is the Riemann zeta function. This is the
okay.
zeta from here.
Okay.
Okay? I just plug this gamma multiplying the zeta function. Okay, and this is very, very important. So, in principle, what is the cost of adding particles to my system in general? Like what do I plug? 0. Like, I can put any number of particles, and still I have a number that, as a function of volume and temperature, I will get a fixed number anytime. But in principle, I can put as many as I want. So what is going on? Do you have any? And it has to do with what you said at the beginning, about this epsilon. Okay. Any guesses? No? Okay, so it took some time to Einstein to figure out, but he was the one that actually proposed that most of the states, as you said, are sitting on epsilon 0. Right? So let me just show you with a plot what is going on. Imagine that we are doing an integral, right? And the value of the function on 0 is like this. And after 0, we have like points that are a little bit above 0 with respect to this point, right? The integral will give us 0. Why? Because it's like if we were doing an integral from 0 to epsilon of some function, and then we are sending epsilon to 0. So at the end, we're counting all the states that are above 0, like from this point on. Okay, but we are missing that almost all the particles are sitting exactly at the 0. So what do we do instead? So we plug this density of states, right? This epsilon as 1/2. The real density of states is that this is true when the states are above 0, but at 0 we have a huge density of states. So we need to put this by hand. So actually what we computed is the number of particles that are above 0, okay? So the actual number of particles should be the number of particles at 0 plus the number of particles at excited states, right? And then how do we compute the number of particles that are sitting on 0? Well, we just need to get this number, right? The occupation average at 0. So you were completely correct. Like if you see here, when we send mu to 1, to 0, sorry, and the fugacity to 1, then this number explodes. So now we understand what happened. Like all our particles went to this level. Okay? This is what is called Bose-Einstein condensation. Just one point. did you remember that when we saw different statistics, and I told you, listen, when you get this minus here, that do not appear of fermions, it's very, very important. So it's the one that is causing this jump at zero. So it's the one that causes some sort of instability of the system, right? Of this function. So that's this is something that only happens in bosonic particles, and all the bosonic particles have this problem. Okay. Do you have any questions about this? Okay. So I'm going to be a bit repetitive, but the thing is that when we are doing boson statistics, when we are computing the number of states, we have to be aware, because at low enough temperature, all the particles want to sit on the same energy level, which is at the ground state, right? And that's something that fermions cannot do, because they cannot occupy the same state. The two fermions cannot occupy the same state, right? Okay, so the idea is that we compute the number of particles at excited states, and we add by hand the number of particles at the ground state. Okay. So now let's see the temperature dependence. So I just told you that at a low enough temperature, then most of the particles will be sitting on the ground state. So now we want to compute and understand below which temperature this happens. Okay. So what would you do in this case? How would you get the critical temperature? Do you have any intuition?
No, you want to find the energy, no?
Or okay, we want to find the temperature when the condensation occurs. So like the point in temperature when this term starts dominating, or the other way around, like the frontier when one of these terms starts winning the competition. Okay. Below some T, this term wins, and above some temperature, like this same temperature, this term is the one that gets most of the contributions. So the way to think of one way to think is that at temperature at critical temperature, slightly above the critical temperature, then the number of particles of the system should be the number of particles of the excited states, right? Do you see why? What? Because a little bit above this temperature, then the most contribution would be coming from the ground state, and the number of particles on the ground state would be negligible.
Like a little bit above the critical temperature.
The critical
already all the particles go to the.
Not all, but most.
Most of them, yeah. I wouldn't tell you that there won't be any particles at the ground state,
But it's
but
negligible.
yeah. What's happening below temperature is that a microscopic number, a huge number of particles are sitting on the ground state, right? So we would have energy levels, and most of the bosons are sitting here.
Mm-hmm.
But when I achieve the critical temperature, then they are allowed to move everywhere. So they have the degree of freedom of moving all around these states. So why would I have some more probability to find them here? Like I would have some probability, but it shouldn't be meaningful, the number of particles that would be sitting here. Okay? Okay, so the idea is that we just need to plug here the critical temperature. So B to MKB TC 3 halves over 4 pi. And from here we can extract the critical temperature. This is the same thing that we do for the Fermi energy, right? But instead of getting the Fermi energy here, we are just trying to compute the critical temperature. So this should be H bar Q over B. Great. So this would be the critical temperature. You can see that it's related to the and here there's a K Boltzmann, right? So you can see that it's related to the energy of free particles, right? And the idea is that we have computed TC, and now let's see how this works. To understand what's going on, let us compute the number of particles on the ground state divided, what fraction of particles are sitting on the ground state, right? This would be this number. Okay, so it would be just n naught over and from here we can take the ratio of T over Tc. So this represents, this n excited is the one that we have at Tc, right? and it's proportional to this term. And below we have t. So this is sorry, just this one minus to the third part. Why? Because we're extracting the t dependence. Right, so we can see here that n depends on tc as a function of 3 to the 2. And all the constants besides the temperature are the same. So when I do the division of these two things, I would get only a ratio of the critical temperature and the normal and regular temperature, right? So let me just plot here what's going on. Okay, so this is temperature, and this is the number of particles. And okay, just show you. Okay, so this is the particles that are sitting on the ground state, and these are the particles that are sitting above on all the excited states. So as a function of temperature, you can see that I exaggerated this region. Actually, this is very, very sharp. Okay, but it's just to show you what's going on. So when we turn on temperature, you can see it from here, right? This is actually this graph goes as T1 over T to the 3/2 over 2. So when we increase temperature, then the number of particles in the excited state starts increasing. So do you remember this plot that I did? So at 0 temperature, everyone's sitting here, right? But when I increase temperature, then the particles are starting to sit here, here, here. And then I get to a point where most of the particles are sitting actually above 0, so they are here, here, and all the macroscopic, all the big number of particles are sitting above the ground state, and maybe 1 or 2 particles are sitting here.
אני לא מבין את ה... מצאנו את TC על ידי זה שהשווית את ה-N של ה-excitation להיות N.
Right.
אבל גם ב-T שגדול מ-TC, הפוך, ב-T שגדול מ-TC זה עוד יותר יהיה נכון.
Right. Okay, that's absolutely true. I just want to... What do I want to compute? I want to compute TC. Mm-hmm. So I just care when is that happening, right? So when it's happening, when all the contributions or most of the contributions are coming from N. So that can be true for any temperature, okay, above TC.
Mm-hmm.
In general, you can compute, you can have N as a function of T of the particles that are on excited states, right? Above the critical temperature, because below you would get a sharp transition.
Mm-hmm.
Okay. Was it clear?
לא,
Did I answer?
אז הנוסחה הזאת שמצאנו ל-TC, שכבר פה של ה-H בר בריבוע, אתה יודע? לא, למטה? זה, כן. אז זה בעצם זה פשוט נוסחה כללית של T כתלות ב-N?
כן, כאילו ב-TC זה N-EX.
Right, but above TC, everything, okay, so we already knew how this looks, right?
Mm-hmm. Yeah.
Like from the beginning of the lecture. So, and now we want to see exactly when the transition comes. When I am lifting all the states that are sitting here upwards to more energetic states. Okay, that's the value of TC, that you have some behavior of the system, and then it drastically starts working in a different way.
Okay.
Right? So, in general, this is very useful. For example, when you are doing vapor liquid transitions, anything, like you want to understand how does the system comes from one behavior to drastically behaving in a different way. So that's what we are looking to right now. Okay. So do you have any other questions? No? Okay. So let's do an exercise. So yeah, this is very huge. Like, think that we're finding a fundamental quantum behavior of something that is macroscopic. Like, you have a microscopic number of particles. We have many, many particles. We can send n to infinity. But whenever we are below Tc, all those particles are having some quantum property that makes them sit at the lower state, which is that they follow Bose statistics, right? So the idea is that, and we actually have seen this on the lab. Like, they actually view this state of matter, and moreover, this state of matter has all quantum properties. So it behaves with the Pauli exclusion principle. Well, not Pauli because these are bosons, but with the Heisenberg uncertainty principle, you can actually see it on the lab using this this system of Bose gas. Okay. And you can measure anything you want to measure about quantum mechanics on bosons. You can measure it using Bose condensation. So it's quite nice. And it's yet another proof that quantum mechanics works. Okay, so let's do an exercise. Okay. Okay, this is the exercise. We want to compute the pressure and the heat capacity of the Bose-Einstein condensate. Okay, let's start with A. So, what would you suggest me to do?
Find the grand canonical partition function.
Perfect. Okay, so we start with this quantity that is a partition function for every energy level, which is 1. So we want to do the connection to pressure and temperature to get some thermodynamical quantities, right? So do you know that the way to gate the partition function to the thermodynamics is through the grand canonical potential? Do you remember what is the grand canonical potential? Is minus PV, right? Because we did a Legendre transformation on the number of particles and on entropy. So the only thing that we have is P minus PV. Okay. It's also KBT this small z is the fugacity. Okay. So from here we can get actually the pressure. So here in this density of states we need to include the fact that we are dealing with a Bose condensation, right? So in other words, we need to separate the integral, so it's kBt over b, right? The rate, I'm going to put here a tag, or maybe the 0, something. Okay. Let me just close the parentheses here. Okay, so we have the pressure that it's the usual partition function for all the states, but we need to include the state when of the ground state, the partition function of the ground state by hand. Okay, we do this like by the way we define the partition function, which is the density of states regular plus density of states of ground state. Okay. Which implies that we are going to solve this thing here. Okay, so let's see what this quantity one so we have 1 over b plus so then I just, in this case, I just plug in the number of particles of the ground state, right? And for a very big number of particles sitting on the ground state, then this doesn't contribute anything to my integral. So this would be 0. And then the pressure is minus k b. I forgot a minus here that is coming from this. And then we need to compute the, like, do you remember that I put the integral at the beginning from 0 to infinity, but from x, I did all the change of variables. You do the same thing and then you get the answer. We don't have any time left, so I'm just going to leave it here because the important part is that you know, like, you see the process of how you deal with the condensed part. Okay. And B, we need to compute the heat capacity. So we would like to find, you know that the heat capacity is the U dt, right? That constant volume. So the way to find actually U is to do, we can do this, actually this integral. So there are many different ways of computing things to gating thermodynamics with statistical mechanics. One is that you can take advantage of the thermodynamical potentials, or you can take advantage that the thermodynamical quantities are just a statistical average over microscopic quantities. So this would be the epsilon. Okay, so here we're just putting the occupation number, and here I have the energy, right? Whenever I want to compute a quantity, right, that I have something that looks like the energy, and this would be any operator, like any thermodynamical statistic, thermodynamical quantity. I can compute it as an average, as an integral over A times the density over the partition function, right? Over the thing that I'm summing up, the A, right? I can always do that. This is just the usual way of defining the average. This is the probability density. Okay? So this is the integral from 0 to infinity. E to n 3/2. This is again, and this is the epsilon. This is again the zeta function for 3/2. So we just have b times 2 m 3/2 over 2 pi h cubed times 3. Sorry, I'm missing a space here. This is just the zeta function of 2.5. Here, what I did here is just I plugged the gamma function of 2.5, okay? So this would be the gamma, this term comes from the gamma function, okay? So once again, let me just plug it in a clearer way here. This would be B and That's fine. And then to get the heat capacity, I only need to do the derivative with respect to t, right? So I will find that this is all. Let me call just all these numbers alpha. So this would be alpha times kb 2.5 times 2.5 t 1.5 times the set Riemann set coefficient. Square root of 5. Okay. Okay, that's the heat capacity and that's the exercise. Do you have any questions about how I computed both the pressure and the heat capacity? No? Everything's clear? Nice. First time I finished on time. Well, 5 minutes later.
Thank you.
Of course.
איפה ככה? נראה לי לחזור הביתה אבל... יש לי מספיק בגדים כאילו יהיה לי ככה. כן? לא, נראה לי שיש...